Chapter 5, Section 2, Verifying Trigonometric Identities, or Trig Proofs. In this section, we're going to start off by continuing to simplify like we were doing in Section 1, and the reason being is because we need to learn a few more things before we start into trig proofs. So on this particular problem, I see that I have two fractions, and so what I need to do is I need to try to consolidate those two fractions into one term. And so when I do this, there's a couple of things that you may think. You may think that we need to get a common denominator and go that route, but when you do, that just makes things more complicated. The other thing is we need to get into complex fractions. So let's just go ahead and start there. So we're going to do 1 over cosine x over 1 over sine x plus 1 over sine x over 1 over secant x. I'm sorry, 1 over cosine x. And then if we do skin over guts, we're going to have sine x over cosine x plus cosine x over sine x. And that writing is horrible, so let me clean that up a little bit. Alright, and so from here you may think, oh, well, that's just tangent x plus cotangent x. Well, we still have that plus sign in there that we need to get rid of, so it's not quite that simple. So at this point, now that I've got things in terms of sine and cosine, I think what I'd like to do is I'd like to go ahead and put the fractions together. So if I put the fractions together here, the common denominator is going to be cosine times sine. So on the left-hand side, to get that common denominator, I had to multiply by sine x, so I need to do that by the top and bottom. So I'm going to get sine squared x here, and here I needed to multiply by another cosine, so I'm going to get cosine squared x. Okay, and so from earlier in section 1, we know from here we're going to get sine squared x plus cosine squared x over that common denominator. So now we have one fraction, so that's a good thing. And we also learned in section 1 that sine squared x plus cosine squared x is 1, so we have 1 over cosine x sine x. And we know that we can split these up and have 1 cosine x times 1 sine x, which is basically going to be secant x times cosecant x. And so that's simplified. We don't have any quotients, we don't have addition and subtraction signs or anything like that. So I think that's as simplified as we can get it. Alright, so let's look at this one. Again, we have two fractions that we need to simplify. And so when we do that, we need a common denominator. So to get a common denominator, we need to multiply those two denominators together. And so basically what we're going to have is sine alpha minus 1 times sine alpha plus 1. And that's a lot of writing, and we know that when we multiply a sum and difference, that's going to give us sine squared alpha minus 1. We get the difference of two squares. And so I think I'm going to let that be our common denominator. So a common denominator is going to be sine squared alpha minus 1. But to get that common denominator, remember I had to multiply these two together. So if I already have a sine alpha minus 1 and I need to multiply by sine alpha plus 1, I have to multiply that 1 times the same thing. So we're going to get sine alpha plus 1 on the left hand side as well. Minus, I need to multiply by sine alpha minus 1 on the top and bottom, so I'm going to get down here sine squared alpha minus 1. Okay, so if I put these together, I need to remember that this minus sign goes this minus sign here goes to both of these terms. So what I'm going to have is sine alpha minus sine alpha, which is, they're going to cancel out. And then I have 1 minus a negative 1, which is going to be 2, over sine squared alpha minus 1. Sine squared alpha minus 1. Well, I know that this sine squared alpha minus 1 from my Pythagorean identities, again, if you have sine squared alpha plus cosine squared alpha is equal to 1, I know that if I minus 1 from both sides and minus cosine from both sides, so I'm just manipulating this. I brought this 1 over here and brought the cosine over here. I know that that sine squared minus 1 is the same as negative cosine squared alpha. So what I have now is 2 over negative cosine squared alpha. And then I can rewrite that as 2 times 1 negative 1, basically, over cosine squared alpha, which is going to be the same as negative 2 secant squared alpha. So again, a lot of manipulations going on. So how do I know that it's simplified? Well, there's no fractions, there's no addition and subtraction, there's just a negative 2 secant squared alpha. Alright, let's try again. When I see this, I see multiplication, basically a binomial squared. And to do a binomial square, remember there is a pattern, but remember what you're doing. You're doing sine alpha minus cosine alpha times sine alpha minus cosine alpha. So remember, you do have to expand it and FOIL it. And so when you do that, you're going to get sine squared alpha minus 2 sine alpha cosine alpha plus cosine squared alpha. Well, when I rewrite that, I know that sine squared alpha plus cosine squared alpha is 1. So I have 1 minus 2 sine alpha cosine alpha. And if you look on your identities page, which we haven't really talked about these yet, so at this point this answer would be fine with me, but eventually, and again it is on your formulas page, you can see that this is actually a double angle identity, and so we have 1 minus sine 2 alpha. So we do have a double angle there. Okay, so we have added, we have multiplied. Now let's undo that multiplication and let's factor. So this is the difference of two squares, and so if I need to factor the difference of two squares, that's going to factor into a sum and difference. So the secant squared alpha is going to go into secant alpha times secant alpha, and then that 1, the square root of 1, is just simply going to be 1, and so that's factored completely. And then if I do 4 tangent square beta plus tangent beta minus 3, that's a trinomial, and that trinomial will factor into 2 binomials. 4 tangent beta, we can break the 4 into either 1 and 4 or 2 and 2, but I also have this 3 here, and there's no way that I can do the 2's and the 1 and 3 to get this 1 here. So I know that it's going to be 1 4 and 1 3. So I can do 4 tangent beta, and 1 tangent beta is what the 4 is going to break into, and then I need a 1 in the middle, so I need a 4 times positive 1 here, and I need a negative 3 here, and so that'll give us our positive tangent on the inside. Okay, this is a cube, and so you have to know the cube pattern when you factor. So I know that it's going to factor into a binomial times a trinomial. The binomial, you take the cube root of each one of these, so that's going to be sine x, same sign, cosine x, and then you're going to have to square that first one, so we get sine squared x, opposite sign, multiply them together, and so we'll get sine x cosine x, always plus square the last, cosine squared x. And again, that's a pattern that we learned in algebra that we need to know. Okay, so that brings us to the verifying identities, and there are some things that we need to discuss. An identity is an equation that states the left side must be equal to the right side. So you know what an equation is from algebra. The left side is equal to the right side. To verify an identity means to prove through substitutions and simplifying, which is exactly what we've been doing in section 1 and in the beginning of this section, that the left side does in fact equal the right side. An identity can be verified either by working with one or both sides of the equation, so that's your choice, again, whichever one comes to you better. And then verifying identities is not the same as solving an equation, so we're not going to be carrying things across the equal sign. Okay, so here's our first one. We have to verify that tangent alpha over secant alpha is the same as sine alpha. Well, sine alpha is about as simplified as you can get it. So what I'm going to do is I'm going to work with the left-hand side and try to get this to equal sine alpha. So I know that tangent alpha is the same as sine alpha over cosine alpha. And I also know that secant alpha is the same as 1 over cosine alpha. And if I do skin over guts, I'm going to get sine alpha cosine alpha over cosine alpha. And since all of this is multiplication and division, I can cancel these out. And so I get sine alpha is equal to sine alpha. And we proved that they are equal to each other. Okay, so let's look at this one. Again, 1 is about as simplified as you can get. So if I go ahead, let's go ahead and distribute this. So we'll have sine squared beta plus sine squared beta cotangent squared beta. And we want to know, is that going to be equal to 1? Well, we have sine squared beta plus, I know that cotangent is the same as sine square beta over cosine. I'm sorry, that's backwards. Cosine square beta over sine squared beta. And we are multiplying, so these two cancel out. And we want to know, is that equal to 1? Well, we have sine squared beta plus cosine squared beta. And we know from the Pythagorean that that is equal to 1, which does in fact equal to 1. And so we proved that. Okay, so with this one, I need to prove that tangent square alpha plus cosine squared alpha minus 1 is the same as these two. So notice I have multiplication here, but I have addition here. So it's not as easy as saying that cosine squared alpha minus 1 is the same as sine squared alpha, and you'd have to do some manipulations anyway. So let's go ahead and fix that. Let's say that tangent squared alpha, and then this cosine squared alpha minus 1, again going off of our Pythagorean, cosine squared alpha plus sine squared alpha is equal to 1. But I need cosine squared alpha minus 1. What is that equal to? Well, if we change these two, we're going to get cosine squared alpha minus 1 is equal to negative sine squared alpha. Alright, and so we have tangent squared alpha minus sine squared alpha, so it's looking a little bit better. So now what we need to do is we need to try to get everything in terms of sine and cosine and see where that takes us. So we have sine squared alpha over cosine squared alpha minus sine squared alpha. And we need a common denominator, and that common denominator is going to be cosine squared alpha, so I need to multiply up here cosine squared alpha as well. Okay, and so what I'm going to have is on top sine squared alpha minus sine squared alpha cosine squared alpha over that common denominator of cosine squared alpha. Okay, and I think what I would like to do now is I have a common term of sine squared alpha that I want to factor out. So I'm going to have sine squared alpha times 1 minus cosine squared alpha over cosine squared alpha. And I know that I can, since all this is multiplication, I think if I do sine squared alpha over cosine squared alpha, that's going to give us this tangent. And I know that 1 minus cosine squared alpha up here, 1 minus cosine squared alpha is the same as sine squared alpha. Again, if we just minus the cosine, from both sides, minus cosine, minus cosine squared alpha from both sides, we're going to have sine squared alpha is equal to 1 minus cosine squared alpha. So just manipulating it into what we need. But what I want to do is I want to separate this into a multiplication problem because that's what I have here. So if I have sine squared alpha over cosine squared alpha times 1 minus cosine squared alpha over 1. And again, you have to agree that if I multiply these out, I'm going to get this right here. So now, cosine squared alpha, or sine squared alpha over cosine squared alpha is in fact tangent squared alpha times 1 minus cosine squared alpha, I just showed you, is sine squared alpha. And so we have our proof. So we verified that tangent squared alpha sine squared alpha is in fact equal to tangent squared alpha plus cosine alpha minus 1 by doing some simplifying. Okay, with this one, I think what I want to do, this looks more complex to me, and when I see this, it looks like I can probably get a fraction out of this because both of these are quotient identities. So let's work with this side and see what happens. I know that cotangent x is the same as cosine x over sine x. Minus cosecant x is the same as 1 over cosecant. No, it's not. It's 1 over sine x. Alright. And of course that is squared, but we're just going to work on the inside for right now. And so look, on the inside I have a common denominator. So I have cosine x minus 1 over sine x. And it's still squared. Alright, from here, again, you need to keep in mind what it is that you're trying to verify. So if you look at this 1 minus 1 minus cosine x, and you see this cosine x minus 1, those are pretty similar. It's not quite there yet because our signs are backwards, but it's pretty similar. So I'm not going to mess with this one just yet. I am going to, however, multiply this out and get cosine x minus 1 times cosine x minus 1 over sine squared x. Alright, so I need everything in terms of cosine. On the top, I've got it in terms of cosine, but on the bottom, I need to get that sine squared x in terms of cosine. And again, I'm going to do that by using that Pythagorean. So I know that sine squared x is the same as 1 minus cosine squared x. And then, so 1 minus cosine squared x, I think if I bring a negative out of this, that's going to give me cosine squared x, yeah. So if we do cosine x minus 1 times cosine x minus 1 over negative 1 times, and that's going to make that cosine squared x minus 1. And it looks kind of like we've messed things up, but we haven't, because what's going to happen from here is I'm going to have cosine x minus 1 times cosine x minus 1 over negative 1 times, that's the difference of two squares on bottom, so I have cosine x plus 1 times cosine x minus 1. And then the cosine x minus 1 will cancel out. So that took care of all my squares, so that's good. So I don't have any more terms that are squared, and I don't need any terms that are squared. So now the bottom, the addition, I can just rewrite, but subtraction I cannot. So what I'm going to do is I'm going to take that negative 1 and I'm going to apply it here. So now what I'm going to have is a positive 1, changing the signs, minus cosine x over, now addition, it is commutative, so I can just rewrite this. So that's going to be 1 plus cosine x, and I think we've got what we need. Alright, so last one. With this one, neither one of these look simplified at all. And so I think what I'm going to do is, I think I'm just going to work over here and see if I can get this to look like this. So, common denominator is going to be these two multiplied together. So if I multiply these two together, it is a sum and difference, so I'm going to get 1 minus cosine square theta. That's going to be my denominator. But on the numerator, I'm going to have to multiply this denominator times this sine theta. So I'm going to have sine theta times 1 plus cosine theta. Minus, and again I'm going to have to multiply this numerator times this denominator to get the common denominator of 1 minus cosine square theta, which is going to be sine theta cosine theta times 1 minus cosine theta. So we're going to have sine theta plus sine theta cosine theta over that denominator of 1 minus cosine square theta, minus, if we distribute here, we're going to have sine theta cosine theta, minus sine theta cosine squared theta over 1 minus cosine square theta. Alright, so let's see if we have any, let's put this together, yeah. So we have common, like terms, sine squared theta minus sine squared theta will cancel out, so that's good. So we have sine theta minus a negative, look, minus a negative sine theta cosine theta, so that's going to be plus sine theta cosine squared theta over our common denominator of 1 minus cosine squared theta. So that's looking good. That looks really good. So now I think what I want to do is I want to factor out this sine theta. And so we'll have sine theta times 1 plus cosine squared theta over, now this 1 minus cosine, and I keep forgetting that S, 1 minus cosine squared theta, again going back to that Pythagorean, that is going to be sine squared theta. And so one of these will cancel out, this sine theta, and one of these will cancel out. Alright, so now I have 1 plus cosine squared theta over sine theta. And so look at what we're trying to get. We're trying to get cosecant theta times 1 plus cosine squared theta. Well, that 1 plus cosine squared theta is what we need. So let's see if we can, look, when we cancel this out, we get 1 over sine theta times 1 plus cosine squared theta. And that's exactly what I want to break this into. 1 over sine theta, which is what happens when I cancel these two out, times 1 plus cosine squared theta over 1. And so we know that 1 over sine theta is the same as cosecant theta, and times 1 plus cosine squared theta. And so we verified that these two are equal to each other. Alright, so again, keep in mind your goal. Always got to have a goal in mind, and that's what we're trying to prove. Work them around, just move things around until you come up to where something looks like what you're trying to get. So I'd like you to try these numbers on page 212 and 213. If you have any questions, which I'm sure you will, bring them into class.